All right. We're very happy to announce the restart of the QGI Seminar series. The first of the series for this year will be Adam Levine. He's going to be talking about seeing the entanglement wedge based on a talk that he gave in March. It's going to be a bit of a new and experimental setup, flipped seminar, where hopefully everybody has watched the talk beforehand and come with questions prepared for this discussion session. So with that, I'll let Adam take it away.
Thanks, yeah. Thanks for inviting me to speak. Yeah, so as Tarek said, this is, I guess, based on a talk that I gave in March. The paper came out over the summer or in September, I guess. I guess that's the fall. I just, if I could say just a little bit before we ask questions, just because I'm not sure if the perspective that we had in the talk was fully the final perspective. So I just wanted to emphasize the final perspective that we had in the paper. The idea was to, I'm just using some slides that I made for a talk last week, actually. The idea was just to try and understand in a different way what sort of separates gravity from quantum field theory, or one of the ways gravity is different from quantum field theory. In particular, we wanted to understand this aspect that it seemed like in a certain sense, you can do better than what causality allows for you in gravity, in the sense that given a boundary region A, well, so let me just remind you of the way this works in quantum field theory first. So in quantum field theory, if we're given access to a time like what I'm going to call a time like 2, which is this region here, if you're given access to the operators and observables in this time like 2, you can actually, it's a fact of quantum field theory that you can actually reconstruct, or I'll say what I mean by reconstruct in a second, but you actually can reconstruct everything in this causal diamond. And what I mean by reconstruct is just that you can write any operator in the causal diamond as sums and products of operators in this time like 2. In other words, the algebra that these operators generate is the whole causal algebra. This is slightly different from maybe what some of you are used to. This involves some kind of space-like evolution. So it's kind of a non-trivial thing to prove, but it is provable. And I kind of wanted to contrast that with the set of gravity. So in ADS CFT really. So in ADS CFT, if you're given a boundary region A, you're given some near a sort of a time like tube, so to speak, of near boundary operators, you can do better than just what people usually call the causal wedge, this WC of A. You can actually see up to the quantum extremal surface. And we wanted to understand this fact, especially in light of recent developments involving islands, where it really seems like causality is sort of being questioned in some sense, or the, what happened, recovering causality is sort of confusing. So we wanted to understand this effect, and our idea was to ask the question, is it possible using simple enough operations near the boundary to act with an operator that sends in some energy whose back reaction causes the region that was previously causally inaccessible to become causally accessible. So either you can see it, so that would correspond to moving this region. So this region that's outside of the causal wedge, but inside the entanglement wedge, it's sort of the extra bit that you get from entanglement wedge reconstruction beyond causal reconstruction. We're going to call that the peninsula. That's a terminology that was used in this paper by Almeri, Mahajan, and Maldacena. But so you can either, our goal was to act with some operator that sent in energy and either moved the peninsula into the past of the boundary region or moved it into the future, but without touching the peninsula. And I'm not sure if it came across in the talk, but one thing that we ended up trying to emphasize was the difference between what we ended up trying to do and say modular, boundary modular flow, which has been shown to do bulk reconstruction, is that in boundary modular flow via the result of JLMS, which says that it's actually equal to bulk modular flow, you actually end up, when you act with the boundary modular operator, you end up sort of acting on the quantum field theory degrees of freedom in the peninsula. Here we were trying to only reveal it via interactions with gravity, instead of literally moving the operator into the causal wedge, if that makes sense. We can talk about that distinction more. Yeah, so I just wanted to emphasize that before we start, if that makes sense.
All right, so does that mean we should open it up to questions now?
Yeah, if you want to.
Okay, the floor is open.
Well, maybe I can ask a question. So there's also this technique that uses the patch map to reconstruct the entanglement wedge. Is there a connection between your construction and this more detailed patch map reconstruction of the entanglement wedge?
Yeah, that's a great question. We, for a long time, tried to figure out what the connection was, because it really does seem like there's a connection. We couldn't figure it out. So let me see if I can say something about this off the top of my head. Sorry. Right, so first of all, let me just say that the PETS map, so naively, one difference is that the PETS map, well, for people that don't know, maybe I should write what the PETS map is. So if you have some operator in the entanglement wedge phi, let's see if I can remember. So you want to do some amount of so the operator of this is equal to, well, what you do is you take phi, you HKLL it to the boundary. So by HKLL, I mean global HKLL, and then you trace out the operator. So you trace out the operator onto your region. So you have some boundary region, right? Maybe I should draw this picture. So you have some boundary region that you're trying to reconstruct your operator onto. Oh, let's call this. This is A and this is A bar. So you do global reconstruction, which maps this operator to everywhere on the boundary. And then you trace out, and then you include some amount of boundary modular flow. Now this is Euclidean time evolution, and our procedure, I guess what I wanted to emphasize was our procedure is really Lorentzian modular evolution, or involves Lorentzian modular evolution. So it's really not obvious to see. So if it were related to the PETS map, it would have to be related to. It would have to be sort of like an analytic continuation to I/2 of our procedure in some sense. So we were trying to do that for a while, but it didn't. Yeah, it didn't seem like it was an exact match. But there were certain things. So let me also talk about something here. So in the talk, I think I brought up this this example, which was where we have, I think I may have switched the regions relative to the talk, but this is this example that was first brought up by Almeri, Mahajan, and Maldacena. So the idea is that if you have these two quantum mechanics systems that are coupled to two baths, and you take a region in the right bath and a region in the left bath, a subregion in the left bath, and now you get some extra bit that's not causally reconstructible from either region, which is the peninsula. And so this extra bit is what you get. So say you just had A1, you would only have this causal wedge. But the fact that you got A2 as well, or that you're giving yourself access to A2, gives you this extra bit. So in some sense, this extra bit is only there because of your ability to act on A2. Now, there is, so one thing in the PETS map that's hard to square with our result is there's this eraser channel, or there's this channel that you're trying to, you need to figure out what the channel is. And what we thought the channel was here was, well, yeah, it's hard from our perspective to figure out what the channel is that we're trying to recover from. Now, something that I've been talking with Faulkner about and other people is on the complementary region, it is more clear. So on the complementary region, say instead I threw something in on this side, right? Now, if I imagine throwing something in on this side, and then including some amount of time evolution up to the time t equals 0 slice. Let me get rid of this. So I'm going to throw I'm going to insert some excitation here and let it evolve up. And then I'm going to delete, so say I start out having access to the whole left, but then I delete some of the left bath. I delete A2. So my eraser channel is getting rid of A2. Then you could ask, how well does the PETS map? So there is a PETS map for that channel. So what it does is it takes, let's call the whole left L. So it takes row L and erases it to row L minus A2. So you could ask, how well can I recover from that map, from that channel? And the PETS map there does make sense. And indeed, the core, like, so so now what you want to do is, for example, look at, say I take a state, let's call this phi L. So I have a state phi L acting on the vacuum, let's say. And I want to measure how well does the PETS map do for this channel when trying to recover phi L. So what the PETS map does is it will actually in quantum field theory language, what the PETS map does for this operator is it takes this operator, modular conjugates it over to here, and then acts with the modular conjugation operator of this smaller region, which then brings it back into here. So it's a map from this larger thing into this region. Maybe people don't know this, but I actually think it's kind of interesting. So have people heard this fact before? So the PETS map, what the PETS map does, so let's talk about PETS map first. So if I have an algebra A1 and I have a larger, and I have a larger, sorry, let's say a subalgebra A2. So this is like in the previous example, it was like I had the larger algebra, which is A1, which is all of L in the previous example. And then A2 was like all of L minus A2, minus this region, which I'm calling A2. These are curly A's. So what the PETS map does is it uses, there's this thing called the modular conjugation operator. So let me call it J. And the modular conjugation operator, when it acts on an operator in an algebra, let's say on some algebra, it sends it, this is an operator in the complementary algebra. So it sends it into its complement. So when I have nested algebras like this, well, the modular conjugation operator, so if I have A1, I'm just going to draw something schematic here. So if I have A2 and then the larger thing is A1. If I start with something in A1, let's say phi here, and I act with the modular conjugation operator, it will send it into the complement of A1. But the complement of A1 is also the complement of A2 by nesting. So when I act with the modular operator of A2, it will bring it back into A2. Sorry, I should mention that these guys, well, yeah, these guys also act on the, so this is true if I, so this is true also. Well, this is an operator in the, so.
Sir, can I ask, can I interrupt you?
Yeah, go ahead.
In the island setup, what PETS map does is maps operators in the islands to that of Hawking radiation.
Yes, that's right. So here I'm describing a slightly more abstract version of the PETS map. I can try and map. I can try and explain how this maps onto the island discussion. But here I'm doing this using language that's suited to quantum field theory, because that was sort of what the goal was in our paper. The PETS map discussion in like the West Coast paper, for example, is suited to systems of finite dimension. But it's a
sir, does it seem to explain where the non-locality is coming in the picture?
I'm not sure. So which non-locality?
Maybe it's not a well posed. It's not a question well posed. It may be a wrong question. I wanted to know the why islands and the Hawking radiation seem to belong to the same Hilbert space. It's justified by the PETS map, but is there a deeper theory with some intuition as to how this non-locality is coming in the picture?
Yeah, well, that was one of the goals of our paper, was to find, I think maybe what you're looking for, or at least what we were looking for, was some sort of more semi-classical understanding, or maybe a more Lorentzian understanding of maybe I should say a Lorentzian understanding of how the information is actually able to get out from the interior. And one way we wanted to go about that was by trying to understand, just in situations in ADS-CFT that we thought we understood what was going on, how is it that the exterior region can access this seemingly causally inaccessible region in the first place? How is that? People like Dan Harlow and other people were confused about this for a while, and part of the resolution was that ADS-CFT is a quantum error correcting code, but we were trying to come up with a slightly different understanding of that.
This same setup seems to be in the ADS-CFT context also. No? Maybe it could be applied to ADS-CFT context, as you mentioned that Dan and his collaborators are working on the in the same spirit, trying to explain ADS-CFT as a quantum error correcting code using the PETS map reconstruction.
Yeah, you can use, sorry, maybe I'm not understanding what you're saying, but you can definitely use the PETS map in the scenarios I'm discussing. You can use the PETS map. And I think Jan's question was, how is that related to what we were trying to do? And well, yeah, I'm not sure, but. But yeah, the PETS map always works. because it's based in quantum information, which is very general. We were trying to do something a little bit more detailed, which is that we're trying to actually understand what's going on semi-classically, which is maybe too much to ask. And in fact, I can explain how that is too much to ask. There's a theorem that says it's, well, there's something in our protocol that breaks down if you try and push it beyond its limits.
Yeah. Thanks.
Yeah. Sorry, maybe this PETSmap discussion is too much, but all I wanted to say in the end was that so the PETSmap is basically, the PETSmap written in quantum field theory language is just basically you can write it in terms of these modular conjugation operators as this. And these modular conjugation operators can be swapped out for Euclidean modular flow. And I won't explain that, but that's true. But so if you wanted to study how well the PETSmap was doing, you would study something like the overlap if you acted this on the vacuum versus you acted the original operator on the vacuum. So you'd look at the overlap between these two states. Actually, sorry. Let's say OA is Hermitian. So you would look at the overlap between these two states, and you'd ask how close is this overlap? How close is this overlap to just OA, right? Let's say we've smeared O, so it has a finite two-point function. Then it turns out you can relate this exact, so this ends up looking something like a correlation function in a quantum field theory, and you can relate that overlap exactly to the correlation function that we discuss in our paper. So that's in the boundary modular flow section. But you can relate it to our correlation function at I/2, at S equals I/2. We studied it on the real axis. So that is very tempting, but we couldn't figure out why. So it does seem like the success of our protocol is related. Well, what we wanted to argue was somehow like the success of our protocol is related to some property on the real line of some function. And we wanted to argue that then we knew some property about that implies some property about the function on the line at S equals I/2, but we couldn't prove anything like that. Anyway, that would be what someone would want to do. Okay. Anyway.
So is your setup mostly aimed at getting in principle things out, or can you, like this PETSmap is also supposed to give some insight in why local quantum field theory might be a good approximation outside the causal wedge, still inside the entanglement wedge? Is that the type of information that's accessible, or is it more like an in principle opening up of the causal wedge to include the rest of the entanglement wedge?
I think it's an in principle opening up. Sorry, maybe I'm misunderstanding your question, but certainly this is not very practical. I mean, you would need to have, so the operations that you would need to implement to do our protocol are very complicated, but they're not, in the language of some people in our field, they're not like exponentially complex. So you don't need to know very fine-grained details of the density matrix on the boundary. You just need to know sort of like the generalized free field degree. Like you could make sense of the density matrix on the generalized free field subalgebra in some sense. That's sort of all you need to do our protocol.
Okay, I see. Thanks. Yeah. Good.
But so then it's no surprise that our protocol doesn't work in general. Like you can't access islands using our protocol, and there's a theorem that says that you can't do that, which is related to an energy condition.
Cool. Thanks.
But so, can I ask a question? So is it a correct cartoon? So You kind of give this example of this Gauss first wall thing, right? Where you act with this O left, O right, and it makes some negative energy.
Yeah.
Can I think of what you're doing as roughly so you wrote, I guess on this slide here, you have this e to the IG O1, 2. So that's kind of the thing that makes the negative energy. And then you might need to sort of like conjugate some operator with that. Is that roughly the picture, or?
That's the picture, yeah. But so our final protocol involved it's sort of just like a fancier version of e to the IG O1, O2. And it involves the density matrices of the quantum field degrees of freedom in this wedge here. Well, in this wedge union this wedge. So sorry, union this region. So it's really, sorry, I should say this whole region and this whole region. It involves those density matrices. Those are, and we're gonna exponentiate those to the IS. So it's like a unitary, similar to this, and it's like a double-sided unitary. So it's a more complicated example of Gauss wall in that sense.
But I mean, to what extent can you get away with these simple operators like O1, O2?
Yeah, so you can rewrite the density matrix. Okay, so in principle, yeah, right, good. So you can in principle write the unitary that we construct in terms of these. So like it's a really hard problem and hasn't been done in general, but for free fields, you know that the unitary we're acting with looks roughly bilocal in A2 and sorry, it looks roughly like something like this: e to the I integral O2 O1 times some smearing function.
This is if you're doing like free field theory in the bulk.
Mm-hmm. Yeah, let's work in the free field approximation. Yeah, so in that case, you know that the answer, the unitary we're working with is something like that. Now, constructing this F is a really hard problem. It's been done in like a couple examples. So, but for a massless, we didn't include this in the paper, but maybe we should have. But for a massless free fermion, this F is known, and it's actually pretty simple. And you can write it down. Now, one difference between our unitary and Gauss wall is that these we can have a discussion about how much this matters, but these O1 and O2 and Gauss wall are really like local operators right at the boundary.
Mm-hmm.
In our discussion, this smearing takes these operators out into the bulk of it, a bit like all the way up potentially to the causal surface. So
but okay, so it's some simple operators in the causal wedge of that thing.
Yes.
So let's say that those things are fine.
Yeah. So, but on the boundary, it's some horrible smearing of operators and stuff. Like you could use HKLL to map those operators to the boundary.
Yeah. And then can you remind me, perhaps things happened partway through your talk that I missed something. So once you have these ingredients, then what do you do to like reconstruct that?
To reconstruct the peninsula or some.
Yeah.
So well, one thing that's kind of a subtle point, which I'm not sure if it came across in the talk, is that we're not totally sure that we can reconstruct. We didn't decide either way. We couldn't convince ourselves either way. But we definitely can see. So the distinction is that we can create an operator. We can create operators on the boundary which have non-zero commutator with operators in the peninsula. That in principle is not the same as, so like going back to this causal wedge, to this.
That's pretty good. I mean, you can kill people with commutators, so. I mean,
yeah. No. But I'm just saying, if you really wanted to reconstruct all the information about the thing, it's not equivalent, right? I mean, just by looking at someone, I can't figure out, you know, what's going on inside of them, for example. You know, things like that. But okay, so the procedure then is just you actually technically, to do this, you have to deform your Hamiltonian by this crazy operator. You just follow the steps of Gauss first wall, and what that does is it creates a shock which sits right at the tip of the causal surface, and it sends in a pulse of negative energy, and that negative energy is enough to when objects that are in the causal wedge, or operators that are in or excitations that are in the causal wedge that are moving out towards the boundary. So this guy is moving out. When it crosses this negative energy shock, it will get a time advance, and it's able to make it out to the boundary. And the size of this negative energy shock is enough to actually get everything out. So everything to leading order in G Newton can be seen in this peninsula. If that makes sense. So so in the discussion in Almeri, Mahajan, and Maldacena, they weren't. They just said, in principle, you can send in a negative energy pulse and get some stuff out. The question was how large. So you can't send in just an unbounded amount of negative energy. That's not allowed. You're at least restricted to keep this causal wedge within the, you know, you can't move this causal surface past this quantum extremal surface. But the question is, could you at least get it up to that? Can you saturate this bound? And the answer was, yes to leading order in G. Yeah.
So the negative energy, it's not just on those green things that you drew there. It's also negative.
This slide let me erase that. Sorry. So in the discussion, Almeri, Mahajan, and Maldacena, they didn't care. They were just saying, act with some local operators here and here, that'll send in a pulse of negative energy. Our pulse really is sitting on this past horizon here. It's a good question, and maybe you could find a different operator that has the same effect without sitting right on the past horizon. If that makes you nervous.
No, I mean, that seems like the most efficient place to put it. So.
Right.
Right, thank you.
Yep.
So does your protocol seem to give any hints to state dependence of the black hole interior?
Yeah. Hints. I don't know if it tells us anything new, but it certainly is consistent with the picture of a state-dependent reconstruction. So the comment I would say on that is that this operator here that we're acting with is very, so our code subspace here is or what people like to say our code subspace is we're basically looking, in this case, for example, we're looking at the vacuum, which is a sort of fixed geometry. And then someone is gonna leave a message in the peninsula for us that we're gonna try and figure out. And the message defines our code subspace, or the possible states of the message defines our code subspace. And
yeah, I'm sorry. Does it seem to give any hint as to why the message can only be decoded within the code subspace and not within the entire Hilbert subspace?
Right, because, well, in our case, what I was going to say is that this unitary that you need to act with needs to be very fine-tuned to the background state. If it isn't, I don't think you'll send in negative energy. In fact, I think in general, you'll send in net positive energy and the message won't get out. So
And
this, you need to take
is
into
it
account correlation.
okay?
Sorry, yeah.
Is it linked? Meaning, why is it so fine? Meaning, what is going at the in depth of it? Meaning, why is so much fine tuning required in this setup that uh, the unitaries that we act will give negative energy shocks for very special classes of states which are in the code subspace. I'm just trying to extend the argument which you gave, that why do we require so much of fine tuning in the setup?
I think so. When you're trying to send in negative energy, that's a very I guess what I would say is that in this case, the way it manifests is that quantum field theory doesn't like to let you send in negative energy in some sense. Like you need to be very careful, and being careful amounts to tuning your interactions to, like, you know what set of states effectively, you know detailed properties about the background state so that you can act with the correct operator.
And why are these operators state dependent? Can we get some insight into this protocol? Into Meaning, state dependence is something which is unusual in the framework of quantum mechanics. So,
Well,
where is inherently coming from?
it's not unusual in the framework of approximate quantum error correction. So that sort of the modern, I would say the modern point of view on that, at least my understanding of the modern point of view, is that state dependence is really like code subspace dependent. So it's like if you have a quantum error correcting code, the encoding map or the decoding map can depend on facts about the code subspace that you're working in. And that's fine. That doesn't violate quantum mechanics. It's just a fact of quantum error correction.
And can we probe its action outside the code subspace?
Oh, that's a good question. I would expect it has no, I mean, it's like you're acting with some crazy, so yeah, so like let's say let's take this operator and map it to the boundary. It's some crazy smeared unitary. I think outside of this state, it's gonna have, I mean, it's gonna send in, I don't even know if it'll have a say you take some excited semi-classical state. I don't even think it'll have a good semi-classical interpretation of what it does in the state. Would be my guess. I don't know. But I don't think it'll do what you want it to do.
Yeah. Okay. So the general idea would be it would be sending some positive energy shock.
You mean outside the code subspace?
Yeah.
Yeah, it's not even clear to me that you could say it sends a positive energy shock. It just does some crazy, potentially not even semi-classical thing in other geometries. Yeah, it'll excite, yeah.
And does Pet's map reconstruction seem to give any insight to it?
To this protocol?
Yeah, to the state dependence issue.
Yeah. Well, I mean, the PETS map depends on the code subspace. What the?
Yeah, beyond the code subspace.
Oh, yeah. Again, if you wanted to extend the, action of operators reconstructed using the PETS map beyond the code subspace, I don't think in general you would know what they do. Well, it's a little bit confusing because sometimes people keep projectors around, so they just sort of arbitrarily set the operator to 0, or not arbitrarily, but they just set the definition of the operator to 0 outside the code subspace.
Okay, thanks a lot, sir.
So in these traversable wormhole papers, maybe Ben knows more about this than I do. I thought you, in principle, large number of light fields in your exponential in order to open up a sufficiently deep throw to be able to send information through?
Mm-hmm.
Conditions show up anywhere, or did you find a workaround of that somehow?
No, we didn't find. No, we need. Sorry, we need that. So our whole paper uses this large number of light fields.
But in like ADS-CFT, the number of light fields is not large. So how do you? I'm always confused how we think we should.
Well, I think isn't the idea that it's like large but not too large, right? Like there's some intermediate scaling. I think you can come up with a model that has some. Well, I'm not sure. Okay. My impression is that you could come up with models that have some parameter that dials the number of light fields in the bulk.
But should construction not be, so your construction only applies to theories that have a certain like a certain light spectrum then, or?
Yeah, yes, that's an unfortunate thing about our construction. Yeah, in some sense it's like it needs like the bulk. It's almost like we're working in this doubly holographic setup. Yeah, we need a large number, basically because we need part of it is that we want, well, so if you didn't have a large number of fields, this peninsula setup wouldn't even really be, oh, sorry. This happens to me sometimes. Hang on. That peninsula setup wouldn't, it wouldn't, so this surface here would be an order G Newton distance away from the causal surface, and it's not clear to me that you could even send even a single bit through because at that point the back reaction effects become large enough. As soon as you send one bit through, it's not clear that it doesn't close off the peninsula.
But let's see. So here to have this big peninsula, you already had to have a lot of bulk fields, right?
Exactly. Yeah.
So then, okay, fine. Once you have those around, then I guess you're allowed to use them in your procedure.
Yep.
But I guess you have some other examples, right, where you have a big difference between the entanglement wedge and the causal wedge that doesn't require a lot of fields, right? For example, when you have these positive energy shocks or whatever.
Right. Yeah. So that's right. We didn't, unfortunately, that part of the paper ends up being a bit speculative. I can explain why that was harder to define, but yeah, that's right. So we wanted to sort of model this as like a generalization also of this paper by Tarek and Ahmed and Aitor. Where they tried to do bulk reconstruction by sort of like deleting positive energy shocks.
Yeah. Our
procedure, ideally, although we couldn't quite make it work, which is for probably a good reason. But our procedure, ideally, what it would do is boost the positive energy shock off to the future. And when you boost the positive energy shock off to the future while leaving the stuff in the peninsula alone, what that ends up doing is it reduces the relative boost between stuff trying to leave the peninsula and stuff and stuff falling in. And so the time delay that's the peninsula, the message suffers due to the positive energy shock decreases. And so you can actually see more and more by boosting away. So they like deleted the shock. We wanted to do sort of like a continuous process for a one parameter family of spacetimes. But defining that directly in the bulk is kind of a hard thing to do in general. But yeah, a natural generalization of our procedure in that case would just be to boost stuff away. I can explain why that's hard in general, but if that's interesting, but maybe I'll see if you have any other.
Well, but so, I see, but so you don't have examples where you're happy with your, I mean, probably that would be interesting to hear about.
Okay.
But you don't have examples where like your procedure works without having a lot of, or sorry, there are some examples where there's a big difference between the wedges without having a large number of fields, but there you're not happy with your procedure, is that right?
Yeah, we're not. Okay, yeah. Let me explain why that doesn't work. I have, or it's not that it didn't work; it's that we couldn't. Yeah. Okay. Yeah. Basically, so the idea was like take this example. So here's an example where we have a shock that's falling in, positive energy shock, let's say. And as you said, this doesn't need to be, you don't need a large number of fields. The issue is that now the geometry in the causal wedge, so our operator so what we wanted to define was something like what we called this co-cycle unitary, or a certain unitary that's defined within the causal wedge. Now, our unitary, in its definition, requires two states. It requires a vacuum, something like a vacuum, and the state that you're going to act on it with. And when you have two states, it's the same. The issue that we ran into is a similar issue to finding a bulk dual to relative entropy in general in ADS-CFT. Relative entropy requires two states. Their geometries might be different, so it's totally not clear that they that the bulk dual of relative entropy is a well-defined object. But the issue here is that the geometry in the causal wedge differs between these two states. Let me see if I can.
The two states are just with and without the shock, or?
Yeah, that's right. The two states in this case would be one with the shock and one without the shock, but the geometry in those two states is different. And so we're really trying to define something like an operator in terms of the bulk quantum fields. And if you just allow yourself only access to manipulating the quantum field degrees of freedom, it doesn't seem like it would be enough just to act on those to delete this shock. Unless this shock was created just by inserting operators using the low energy quantum field degrees of freedom, but then I think you are limited in size between the peninsula, and the size of the peninsula is then limited by the number of light fields you have around, right? Because I mean, the stress energy of this is only ever going to scale with the number of light fields, the shock. But in general, if you make this shock like size, if the T++ here is size like order 1 over G Newton, then yeah, we can't say anything about that.
Mm-hmm.
What you can say is boundary modular flow. So our construction has a really natural boundary thing that you can do, and that works. That like works, but it's not new. It's not. It's just Faulkner-Lukowitz basically. That was, and that's what works in this case. And the way it works is similar. What it does is it literally boosts. It takes this thing and it shifts it up in time. So that stuff here it has a lower relative boost.
Mm-hmm.
But you really need access to the full boundary modular Hamiltonian. Yeah, if that makes sense.
Can I ask a question?
Yeah.
So one thing that I wanted to ask about is that your construction seems like it really requires some details of being in 2D. Like there seems like there's some conspiracies that happen. One is that you need the generalized entropy to be captured by this dilaton, and then the fact that the dilaton changes by an amount that's proportional to change in the mutual information, and then the fact that that can be related to the stress tensor. Do you think that such these things could be generalized to higher dimensions in a?
Yeah, I don't know if so this case, sorry, this case here, there is a natural analog of this to higher dimensions, and it works there. So the idea let me draw a picture. So in higher dimensions, like in ADS3, let's just do ADS3 for example. You could have a situation like the following. You could have a bunch of, you could take your region to be a union of a bunch of disconnected intervals, each of which has their own causal wedge, sorry, I'm taking the bulk geometry to be pure ADS now.
Mm-hmm.
So the global state is the vacuum. So each of them has their own RT surface, which is also their own causal wedge. And each of these regions in higher dimensions could be like, now, if these regions are all small enough such that no pair none of them are on one side of they're all on the disconnected side of the phase transition, then there's actually going to be a quantum extremal surface. The quantum extremal surface will look like a union of a bunch of disconnected pieces, but they'll all be slightly larger than their respective causal wedges. And there's an analog of the unitary that we acted with that will put a shock along, it will sort of put shocks along these surfaces moving out. And the shock will have the right size. Well, we showed that the shock has the right size to get operators in here out. So that example works in higher dimensions.
But don't you also have an example like this where like the extremal surface is very different?
You mean like if you mean in vacuum or in
well, I don't remember exactly what you had, but
so
I guess it's just on the other side of the phase transition from this.
Yeah, right. So if we look at I think I did end up talking about that, but I think right. So let's say this is in the connected phase. Our procedure, because we're ended up only acting on the low energy, like on the light field freedom, our procedure will only ever get you up to this surface. It can't get you beyond this surface. What can get you beyond the surface is boundary modular flow. So boundary modular flow, I think this is maybe one of the things that changed between the talk that you watched and our final understanding. So maybe let me slowly on this. So the difference, so boundary modular flow, so the density matrix, let's call this A1 and A2. So the density matrix, rho A1, A2. If this is the boundary density matrix, its action on the state is equal to rho, let's call this whole region little a. So that's the full entanglement wedge. So it's equal to so boundary modular flow is equal to bulk modular flow. This operator has, as a quantum field theory operator, does not commute with things in here, but it doesn't commute because of interactions with gravity. It doesn't commute because it doesn't not commute because of interactions with gravity. It doesn't not commute because of quantum field interactions. We were looking for something that creates a pulse of negative energy whose back reaction causes the increase in the commutator between right. So we didn't, all I wanted to say was that I think maybe when I gave the talk, we were still thinking about trying to understand a semi-classical picture for boundary modular flow in the bulk. but I'm not sure that well, it exists in the sense that we know what the action of this operator is, but it doesn't have a causal interpretation from the point of view of a bulk. We're trying to think of it as like, say I'm a bulk observer and I'm confined to the causal wedge. How would I explain the fact, or what can I do operationally that could allow me to see more of the entanglement wedge? And boundary modular flow is a totally non-causal thing to do as a causal wedge.
Mm-hmm.
I mean, it requires access to operators in the.
Yeah.
I have a question. I was wondering if you could comment more on the energy conditions in this case, because you have this negative energy pulse that is controlled by quantum field theory. So in my mind, that's more like a quantum inequality type of thing. But in the talk, you also mentioned other quantum energy conditions, perhaps QNAC. Could you say a little more about that?
So right. So in this case, let's go to this case where it's not on the connected side of the phase transition. In this case, there's a theorem that says that if you have a region in ADS-CFT, the causal wedge for that region always has to be contained within the entanglement wedge of that region. And that follows from a bulk energy condition. So there's a bulk energy condition called the, well, it's not really, it's an energy condition, although when I write it, it might not seem like an energy condition, but it's called the quantum focusing condition. And maybe you're familiar with the classical focusing condition. So the classical focusing condition says it, well, it's you use Raychaudhuri's equation. And Raychaudhuri's equation says that the change, so if I have some null congruence, it has some expansion. This, you know, if I have some codimension 2 surface, I send light rays off the codimension 2 surface, right? So let's say this is my codimension 2 surface and I'm sending light rays off of it. They move, if they're moving towards each other, then the area of this surface is decreasing. So its theta would be negative. And now Raychaudhuri's equation says the second derivative of the area has a definite sign, assuming that the stress energy, so the formula looks something like this. There's also a shear squared term, but let's ignore that for now.
If this is for me, I'm very familiar. You can move to the.
Okay, sorry. Good. So this is the classical focusing condition, and it's equivalent to the null energy condition. In quantum mechanics, there's an upgraded version of this. So you can define what's called quantum theta, which we usually denote as a classical theta, which is equal to classical theta over 4g plus a derivative in the bulk entropy. And the region that you're computing the entropy for is the region bounded by this codimension 2 surface. Okay. So it's, you compute the density matrix for this region and you look at trace rho log rho, and then you can compute what happens to the von Neumann entropy as you change this surface. So say as you evolve this surface forward in time along a null congruence. How does the bulk entropy of the region bounded by that codimension 2 surface change? And there's a quantum, well, there's a conjectured condition, which is that theta dot is also negative. And if you write out what this says, in the same way that this was equivalent to a null energy condition, this inequality implies a quantum null energy condition. And it says that the expectation value of T++ has to be greater than or equal to the second derivative of the bulk entropy, roughly. Where there's, and this can be negative. So it's no longer lower bounded by 0. It can actually be negative because of quantum effects like the Casimir. The effect that we're talking about is actually very much related to the Casimir effect. So the Casimir effect happens because you're identifying, it's like you have a quantum field theory on an interval, identify the endpoints. In Gauss-Jeffers wall or in the protocol we're talking about, we're coupling the two endpoints in some sense, and we're sort of creating at a moment of time, some sort of Casimir negative energy.
So you're assuming the quantum focusing condition in your...
Yeah. We're always assuming. Yeah, sorry. We're always assuming quantum focusing. Pretty much everything I do assumes quantum focusing. Which has not been proven. It's been proven in certain limits.
And have you checked ANIC in this case?
Yeah, so the ANIC is violated in the states we're working in. So in the same way that in Gauss-Jopres wall, the ANIC is violated. So in this case, so in I don't know how familiar you are with Gauss-Jopres wall, but in the ANIC, if I integrate the stress energy along this, sorry, in this case, I guess I would integrate along here. So T++ integrated along this null horizon. This negative energy shock here is enough to make the ANIC along this horizon negative. Now, you need to make sure that what you're doing is deforming the Hamiltonian. If you don't Hamiltonian, meaning if you evolve forwards and backwards, then there's actually a positive energy. There are some positive energy shocks which fall back from this region here. And if you evolve forwards and backwards, those contribute to T++ along this null horizon, and they're actually enough to make the ANIC positive. But what we're doing here is sort of gluing one geometry is sort of you're sort of gluing one geometry to the next.
But the thing is that these are coronal geodesics, right? So
that's right. So it's not mine. I mean, the coronal ANIC is not.
Seems like we've had a mass exodus because everybody had to go somewhere at 4. I can stop recording and then we can keep the discussion going if everybody wants to. Is that okay?